All right, this video is going to be about notes 28, Calc AB notes 28. It's L'Hopital's rule again. So these are L'Hopital's situations that would not appear on the Calc AB exam. They might appear on the Calc BC exam. I haven't seen one in a long time that requires these techniques, but I think they're in the syllabus, so I think they could show up. If you are looking for something that's way more likely to be on an AP exam, then check out notes 8, which I haven't yet done all of the videos for, but the notes exist, and there's a playlist of examples, and that would be a good place to start. So if you're looking for L'Hopital's rule for the first time, that's a good place to start. Those deal with 0 over 0 and infinity over infinity. These are going to deal with other weird scenarios. So we're going to look at things that look like this. So they look like 0 times infinity. So remember, it's not actually 0. It's a number that approaches 0 times a number that approaches infinity. And like weird things can happen there. 1 to the infinity, same scenario. It's not actually 1. Like the actual number 1 raised to the infinity power is 1. But this is a limit that approaches 1, and that's a different ball game. 0 to the 0, all kinds of issues there. Infinity to the 0, like who wins? Does 0 win and you get 1? Does infinity win and you get, I don't even know what you get? A lot of things going on. So these are all pseudo indeterminate forms because we can make them into 0 over 0 or infinity over infinity. And that's what we're going to try to do. So let's see what we're dealing with here. So immediately you should think like, what would direct substitution give me? But this is an interesting one because you kind of like can't substitute infinity, but you can like mentally substitute infinity, right? And just think like, what would happen? So x would approach infinity for sure. And then 1 over x is approaching 0, so it's the sine of 0, and then the sine of 0 is 0. So this would be infinity times 0. 0. Okay, so that's not a strict L'Hopital situation. But what if we algebraically manipulate this thing? So what I'm going to do, and this is an incredibly common thing to do, I'm going to invert one of the factors. So the factors are x and sine of 1 over x. I'm going to invert one of those. Which one of those would you rather invert? It's not really hard to choose. I'm going to invert the x. So what I'll do is this. The limit as x approaches infinity of, so it's sine of 1 over x over 1 over x. Okay, so how is that equivalent? Because like a over 1 over x is just x times a. So in this case, a is sine of 1 over x. So simplified algebraically, you go back to the original. The advantage here, though, is if we think about both of these, so there's like AP quality work, and then there's the work that I'm going to do here. So the AP quality work, I think what we would do is we would say, so I'm going to put it over here, I guess. We would say the limit as x approaches infinity of sine of 1 over x equals the limit as x approaches infinity of 1 over x equals 0. Therefore, L'Hopital's rule applies. And then after saying that, we would go over here and we would say this is equal to, so by L'Hopital's rule, the limit as x approaches infinity. So this is a really common type where you have a trig function with an argument, and then you end up by manipulating it with the argument of the trig function kind of in the denominator. What's nice about that is the chain rule, right? So we're going to find the derivative of the top, cosine of 1 over x, and then chain rule, so times negative 1 over x squared over the derivative of the bottom is negative 1 over x squared. The chain rule kind of like knocks out the denominator. So this, before we try to do anything, we can algebraically simplify, so we should. The limit as x approaches infinity of cosine of 1 over x, and then cosine of 1 over x, as x approaches infinity becomes the cosine of 0, and the cosine of 0 is 1. So the answer to this question is 1. That's the limit. So it started out as infinity times 0 or 0 times infinity. When you see that, you're going to want to try to invert something to create 0 over 0 or infinity over infinity. You could invert whichever one you choose. It doesn't actually make a difference. So I chose to invert infinity, basically. And inverting infinity gives you 0, so that's how we got our 0 over 0. So we have our good-looking work on the right-hand side, and we have the work that I actually do on these on the left-hand side. You know, it depends on the context of the problem. Like, what are you trying to do with this? So let's look at this. You might need a refresher on the natural log. So this radical x, why are we approaching from the right? Well, it's a domain issue, right? Because radical x, the domain is x is greater than or equal to 0. Natural log, the domain is greater than 0. So like you can't approach from the left, and you can't just approach 0. It's got to be from the right. So this square root of 0 is 0. And then natural log, if you graph it, looks like this, right? So that's going to approach negative infinity. So this is another scenario, right? We have 0 times negative infinity. I want to invert something. I can invert either of them. You want to be careful though. If you invert the natural log of x, you get, you know, radical x over 1 over natural log of x. The derivative of 1 over natural log of x is way more complicated than you might initially think, right? Because it's really natural log of x to the negative first, so it's negative natural log of x to the negative second times the derivative of natural log. It's just bad. So I'm not going to do that. I'm going to invert. Basically, if there's a power function, I'm going to invert that like every chance I get. So here we go. Limit as x approaches 0 from the right. We're going to keep natural log here, and then I'm going to invert. So I'm going to get 1 over. I'm going to get x to the 1/2 because I would always prefer to take the derivative with rational exponents. So this by L'Hopital's. So here's the work that I usually do. I usually write like a little, we'll hope it here. Oh, I'll put a little of that so that the reader knows that I use L'Hopital's rule, and that's why I'm asserting that these are equal. Limit as x approaches 0 from the right of the derivative of 1 over, of natural log of x is 1 over x, jumping the gun. And then the denominator, I'm thinking of it as x to the negative 1/2. So the derivative is negative 1/2 x to the negative 3/2. Okay, what does this simplify to, right? So before anything, I'm going to kind of simplify this. So this is going to be the limit as x approaches 0 from the right still of, so what should we do here? I'm going to think of the denominator, the current overall denominator. I'm going to think of this part as negative 1 over 2x to the 3/2. And the reason I want to think that is that this will simplify to 2x to the 3/2 over x when we simplify it. So this becomes the limit as x approaches 0 from the right of just 2 root x, which is definitely 0. So we get that this limit is 0. All right, so what are we doing here? We're getting 0 times infinity or 0 times negative infinity, whatever. You want to invert one of them. When you get 0 times infinity or 0 times negative infinity, invert one of the two factors, and then it will become L'Hopital's, whatever that is. Something you can definitely use L'Hopital's on. So that's what we want to do there. Should we check this on the calculator? I guess so. I mean, I'm feeling pretty good about it, but you never know. Also, that's the kind of thing you just don't want to say before you go to check. Let's check the limit. So you could use a template. I'll use the template. I don't know if I've ever met you before, you know, so I don't know if you know the things that we do. Infinity is in the pi key, pi, and that gives you infinity. X times sine of 1 over x, and we get 1, which is what we got, thank goodness. And then the other limit was the limit as x approaches 0 from the right, so we put a little plus of the square root of x times natural log of x, and we get 0. So we're good to go on both of those. All right, I'm gonna do, should I do one more example? Let me see what's on the next page. I'm gonna do one more. I'm gonna finish this page. So this one though, gonna look a little different. So follow along as we do it. All right, so you look at it and you're like, I'm gonna try to find this limit, right? Why are we going 0 from the right? Well, potentially 1 over x has different limits as you approach from the right and the left. I tend to look at these and I think like if there's no really compelling reason, it might be because we're going to use natural logs. So if you just think it through, this kind of becomes, what's 1 over x doing, right? So 1 over x, it's like this, it's like this. So as x approaches 0 from the right, 1 over x approaches infinity. So this is basically 1 to the infinity. All right, 1 to the infinity. How are we going to change that into something that we can use L'Hopital's on? Let's see. So I'm going to use a let statement. I'm going to say let y equal 1 plus x to the 1 over x. Okay, why would I do that? It's not really clear initially. But I'm essentially just trying to find the limit as x approaches 0 from the right of y. Like that's what my goal is here. I'm going to, for reasons that aren't obvious initially, take the natural log of both sides. So this will become the natural log of y equals the natural log 1 plus x to the 1 over x. Okay, what can we do with natural logs? Well, exponents become coefficients. So now we're going to just work on this right-hand side here. So this, the natural log of 1 plus x over x, or 1 over x times the natural log of 1 plus x, however you want to think of that. You should think of it this way, though. All right, so that's the natural log of y. Okay, so what's happening here? I say okay way too often. I'm aware of that. I also say so too often. Those are two words. They're just in there. I can't get rid of them. All right, I'm going to take the limit of both sides as x approaches 0 from the right, right? Because that's what we're supposed to do. Limit as x approaches 0 from the right of the natural log of y. Should be, since everything is equal, this should work. From the right of the natural log of 1 plus x over x. Okay, let's half ignore the left-hand side. The one thing that I'm going to use here is I'm going to use property of continuous functions. So natural log is continuous from 0 to infinity, which means that I can take a limit and I can move it inside the natural log. And you do this all the time. You don't really think about it. I'm going to say that the natural log of the limit as x approaches 0 from the right of y is equal to the limit as x approaches 0 from the right of natural log of 1 plus x over x. All right, how is this getting me anywhere? Well, what happens on the right-hand side? So if x approaches 0, then I will get the natural log of 1, which is 0. Why can't I make it a 0? 0 over 0. That's 0 over 0. I can use L'Hopital's on that. Okay, so I'm going to, but I'm going to like stop working on the left-hand side because that's kind of where I want it at this point. So we're going up and over. I'm going to say that the natural log of the limit as x approaches 0 from the right of y is equal to, now I'm using L'Hopital's rule, and it's not like super abundantly clear that that's what I'm doing. So I'm going to say the limit. So I'm just going to do it and then say by L'Hopital's. X approaches 0 from the right. What is the derivative of natural log of 1 plus x? It's 1 over 1 plus x. 1 over 1 plus x over, what is the derivative of x? It is 1. Okay, I'll say by L'Hopital's. Just to make it a little more readable for the reader, who is probably you. All right, so the natural log of the limit as x approaches 0 from the right of y is equal to the limit as x approaches 0 from the right of, if we simplify this, 1 over 1 plus x, which is just 1, right? Because I let x equal 0, and there's no problems with doing that. So we get this. All right, we're almost done. So the most common wrong answer here amongst people who are doing it mostly right would be to say that this limit is 1. This limit is not 1. This is the natural log of the limit. So here we have the natural log of the limit as x approaches 0 from the, it doesn't like making zeros. What am I even doing? Get out, go away. All right, got it, maybe. 0 from the right of y is equal to 1. Okay, exponentiate, right? You got to get that thing outside of the natural log. So the limit as x approaches 0 from the right of y is equal to e to the first, which is e. So this limit, so let's write the original. We'll say, therefore, the limit as x approaches 0 from the right of, what even is the original? 1 plus x to the 1 over x is equal to e. And we did it. So what were the key steps? The key steps, the perhaps the keyest of all steps, is when you get this, you want to do this, right? And the reason that you're going to do that is because then you know that you can take natural logs of both sides. So that's a big deal. And then use properties of natural logs. The next big step is realizing that natural log is continuous, so you can do this. And then finally, at the end, the most important thing to remember is that the answer wasn't 1, that was the answer to the natural log of the limit. And so we exponentiate and we get that that limit is e. Should we check that? I mean, I'm pretty confident that that's e. But let me make you more confident. Limit 1 plus x to the 1 over x, x approaches 0. From the right, you put like a 1 here. And we get this, we get e. Which is maybe surprising, but maybe not so surprising if you think about the definition of e that you maybe learned at some point in your life. This is a different way of thinking about that limit. But anyway, I'm going to go back to the notes, give you some screenshotting moments, and then call this video a wrap. It's probably long. I probably should have, like, when I was, you may recall a while back, I was like, should I do this? Should I not do this? I probably shouldn't have. So here we go. This is our first one. This was a 0 times infinity, invert one of them. That's good. Next one, this was also a 0 times, well, negative infinity, but basically the same. Invert something, create a L'Hopital situation. Here, I probably should have highlighted that. Look at that, I got it in a box. What's a good color for that? Maybe this one? This is not a good color, but it's what we're going with. So we have this. All right, and then here, screenshot this one. This is when we got 1 to the infinity. You're going to want to take a natural log and then go to work, basically. All right, I'll be back in the next video to do probably the rest of these, unless one of them ends up really, really challenging, in which case we'll break it up. But anyway, I will see you then.